Our next speaker is Zsolt Torfi, who is a senior generative AI solution architect with over 25 years of experience in software engineering, spanning leadership roles at global technology leaders, including Microsoft, Telenor, and General Electric. Currently at Nokia Networks, he specializes in designing and building agentic AI solutions that integrate cutting-edge AI software engineering practices, architectural design, and advanced developer tooling. His work bridges deep technical expertise with strategic innovation, driving transformative AI capabilities in telecommunications infrastructure. The title of the speech, Architectural Blueprints for AI Agents. Please welcome on stage with a huge round of applause, Zsolt Torfi.
Hello guys, pleased to meet you. I'm here to represent Nokia Networks and the whole private network solution division. We are 2,000 people, and here we have an R&D organization. And I spent with a small AI dev team the last year or more building and designing AI agents for industry vertical dedicated solutions. Just a question: how many of you guys has ever tried to build an AI agent? Just curious. Did you find it easy? Yes, not that much. So this is exactly the topic of this presentations. Before I dive deep into agentic architectures, let me just introduce what we are doing. Imagine Nokia Networks provides voice and data connectivity, but also we are providing end-to-end solutions for all industry verticals, energy, operations, trains, transportation, mines, where private network, on-premise, and private cloud services and solutions are needed. And you can imagine we are building highly complex legacy telco plus cloud native distributed IT services, and they are quite complex. So just if I pick one of the network functions, imagine one function, which is a collection of containerized services, has a configuration file that contains 27,000 configuration entries. So you can imagine the complexities of the systems, and we are facing with the scaling problem and the efficiency problem. Simply, we don't have enough engineers to manage, plan, operate, fix, support the networks, and somehow we need to find out how to utilize agents to make engineers more productive, but also to embed maybe autonomous multi-agent solutions into the network. So that's what we are doing, and I would like to talk about with one demo in a specific scenario what we exactly building, but you can imagine we are building tons of agents that are focusing on engineering efficiency. Like for instance, we are building a highly knowledgeable system architect that is knowledgeable about the complete network architecture, all the support and failures, all the customer documentations, and we are building knowledge graphs, which I would like to show you in a demo during the session behind agents. And yes. So we are building tons of agents and focusing on CLI-based human in the loop kind of agents, but also we will build background running autonomous agents in the future. Okay, let me just show you an example. Hopefully my VPN works, and let me show you a real system. I am logged into a Linux host, and on the right it is just running the network services. I don't want to bore you with the infrastructure, but on the left, imagine that built into the same network service there are agents, and I can run sessions with those agents, and they are focusing on the network service instance, and basically I can do my job. And let me show you. If I just start up a session, imagine that it will be an enterprise voice core config session, and Yeah, I will copy just some prompts. I don't want you to bore you with my typing. And imagine that embedded this into this network function, an agent will be running. So there is an intention manager logic inside the application that understands the human intentions, and it is just starting up an agent which we call basic. And it is looking at the service itself, but it has a knowledge base, a knowledge graph. I will show you how we build the knowledge graphs behind the agents and how it looks like. It's very, very interesting. But the responses from these agents are coming not just from a vector DB, but it's a true knowledge graph that is representing all knowledge and the system world, the realities of the service. So I can just keep talking to the agent, like I can ask, okay, what's your knowledge? And let me just copy. And you will see that it will provide from the internal operation manual the capabilities. I don't want to go that deep. I hope you can imagine what agents are. I imagine you are building something similar. But we learned a lot when we started to build those kind of agents. And just to summarize what we learned in 2 points, I don't know what is your experience with building AI agents, but we just try to use LangChain, Llama Index, even the latest framework that we use is called Atomic Agent Frameworks. There are so many open source, really nice agents, but they are using totally different abstractions. And we just realized that for industry strengths, really advanced agents, somehow we need to avoid generic frameworks and we need to come up with our own agent hosting logic, orchestration logic, and also an agent architecture concept. So this is the number one learning, and I believe that you should follow that way immediately when you try to build not just a general purpose agent and you're not just playing with open source frameworks, but really you want to embed an agent into a real highly complex system. The other learning, and there is a huge discussion in the industry, what is the knowledge base? What is the content that is providing context for the agent operations? And we just learned, and really I can tell you, we tried thousands of PDF files, architectural documents. We really tried to inject Confluence pages, Jira content into vector DBs. We played with different vector DBs as well, and it turned out that this semantic similarity method, which is called this RAG method, is simply not enough. So you need to invest into building a deeply connected knowledge graph that will provide not just similarity content, but also provides deep contextual relationships to agents. So those are the two learnings that we experienced, and based on those learnings, we are designing a telco-specific AI agent architecture. So let me just dive into this simple, stupid question: what is an agent really? This is our definition. So we believe that an agent, an AI agent, is a kind of semantic execution logic. It's like an integrated service. So still we are talking about a class that takes a structured input. It is doing some operations. It is generating a structured output, but in a semantic way. What does it mean? The agent inside can analyze intentions, can analyze environment situations. It can make decisions. It can plan, and it can select the right tools, and even it can execute the right tools. And it is a semantic execution unit, because sometimes you need to combine LLM-based calls but still build native code, and you need to somehow combine the tools, and this is what we call the worker logic of the agent. Then also it is an important part of the agent definition is that when the agent runs, it has an environment. It has an environment that is precisely describing the world the same way how humans understand the world. So you need some kind of graph approach to represent the environment for the agent when they operate. And sometimes they fetch information, they traverse the graphs, but also sometimes when they are doing the sessions with humans or running autonomously, they are creating new knowledge and they are evolving the graph. So I believe that's a key understanding, is that when you build an agent, think about the environment, how it is represented, how the agent is connected to the environment, and how you get context, but also how you give back, information to the environment. And also, agents sometimes triggered by human intentions. So just another example in our telco case, imagine the Formula One event, and there are 100 VIP person who needs an extra and dedicated bandwidth in the same public telco networks. And you have 5 minutes to provision the slices dedicated to the devices. And you need some kind of autonomous agents that are triggered by humans. Because someone from the sales team just decided, okay, let's give to 500 people a dedicated, highly reliable bandwidth for their devices. But the rest should use the public quality services. Those are human-in-the-loop kind of agents, but many times agents are triggered by system events. So imagine when a failure happens, at the moment, humans should take care of it. We create a support ticket in Jira, it will start a workflow. There are layer 1, layer 2 support organizations, and there are architects and pure developers who need to fix the services. All steps are human-related steps, but can be autonomous. So we imagine that when a failure happens, a troubleshooting agent can be triggered automatically, and it is understanding everything, all the logs, all the environments, all the context of the service, and they are doing by themselves their job, so they can run autonomously. Also important for the agent understanding is that agents should somehow run somewhere. So you need to define a host. A host, typically, it's a chat-based front end, but it can be the system itself, as you saw in the demo. The system itself can host agents, and the host is responsible for the orchestration. It's a whole different topic, how agents should be orchestrated. What are the different patterns? I advise you to read the Anthropic blog. I don't know if you read it, which is nicely describing the different patterns of agentic orchestrations. We experienced there are 3 important topics or patterns. The first one is that there is an event, maybe a human or a system event, and there is a router that can understand, okay, which agent should we start? And from that point, an agent can take it over, and it can understand, but also it can realize that he or she cannot do everything. And then the agent can make the decision to get another agent, so we can change agent together. That's one typical pattern. It's a linear or sequential execution of agents. But sometimes you need to parallelize, because you know that you need to do this thing here and that thing there. So you need some kind of parallel logic. But once you parallelize the agent execution, you need to synthesize, okay, what happens in each agent. So you need to build not just the executor and the worker agents, but also you need to implement a synthesizer agent as well. And the third one is interesting as well. When it comes to reasoning kind of agents, usually some agent is doing some job, but that specific agent cannot check or validate its operations. So you need another agent that is observing what the other agent is doing and qualifying. And usually you start an iteration loop. You say that, okay, I give you agent 5 rounds, 5 iterations, to try to complete the task, the goal that I give you. And there is an observer or an evaluator agent that makes the decision. And sometimes within 5 iterations, the jobs can be done, or sometimes it cannot. So those are the relevant and very typical orchestration patterns. And very importantly, as I mentioned, that the real agentic logic or the semantic execution is about analyzing, planning, and executing actions. So this is where you need to somehow build a worker logic, and you need an operation guide, you need a good context, and you need an environment information to really to create an agent that is equal to a human. So the same way how a human makes a decision, makes a plan, runs commands. Just another example, in network operations, when we need to provision a service, then we need to understand, okay, which host should we use, what kind of SSH sessions should we open, what kind of bash scripts should we run. So all things should be somehow defined the agent. Similarly, how network engineers are understanding, okay, how to operate a network. So the environment is really key. I will talk about the graphs in a minute, but let me show you our agent architecture. So this is how we imagine to implement all kinds of agents, and each block is, I believe, it's fundamental. This is our learnings. In the industry, people are talking about some part, but imagine that finally it is a class. Maybe it's a Python or a .NET or C# class implementation, but it's an abstraction that has very important elements. So one element is, I will tell you, the operation, the identity. What is the agentic logic identity? Then what is the memory? I will tell you that there are different approaches for agentic memory implementations. How you would like to connect to environment. Maybe you are just okay with let's say a Milvus vector DB, but many times I would say when you build serious agent, then you need a graph. And also sometimes you need to calculate or fetch real-time information, maybe from the internet. Maybe you need to run real-time queries from SQL databases. So sometimes you have an environment that you are injecting and building and evolving, and sometimes for certain situations you need to generate real-time context. So you need an environment provider and you need a context provider as well. And also the question how to implement a toolbox for an agent, it's an important part. How many of you tried the MCP technologies, MCP servers, clients? Then maybe you know what we are talking about. For sure, you can build tools into agents, but it's always better to externalize and generalize it and provide some mechanism for an agent to discover external tools. So those are the important ingredients, and I would like to dive a little bit deeper into each part. The first one is the operational manual, and by design we call this an operation manual instead of just a collection of prompts. So imagine it's a documentation, and we just realized that at least 3 areas should be covered with this in this operational manual. The first one is the identity. You need to tell to other agents or hosts how come an agent can be invoked. How can they understand that they are the best agent for a certain intent. So you need to define the identity where you describe the capabilities of the agents. You define the scope of the agent, very important, because you need to tell that sometimes an operation is beyond the scope of an agent. So that you should define it, and also how to identify, because some logic, we call it the intention manager inside the host, should understand the human intentions and find and pick the best agent, and somehow it should be part of the agent definition. By the way, you can imagine when it is implemented as a Python class, then if you are really smart, then you implement like a repository pattern where the operation manual is stored externally to the agent. What does it mean? The agent, every time when the agent runs, it can load the latest operation. It means that another agent can even change the operation manual of another agent. You can imagine an agent can build another agent. So always tries to make it extensible and externalize as much the agent implementations. Inside the operation part, I believe there are three important elements. What is the purpose of the agent? What are the expectations of the agent operations? Very important, because you need to evaluate how good is the behavior of the agent. And also you need a kind of detailed description how to work with the other elements, how the agent is connected to a graph, how the agent is using an external content provider, let's say a Google search provider, for instance. And the third one, maybe it's new to you. We went into this topic quite deeply. We truly believe that when you define the agent in the operation manual, you need to define a so-called ontology. Have you ever heard this term, ontology? Someone? Yes? Imagine it's a schema for the word, should I say. So somehow you should define what the word is for an agent. So for a troubleshooter agent, the word is a collection of logs, tabular data sets. And the word is a network function. So you need to describe it. Or in another case, if you build a knowledge expert like an architect, that architect agent should know and read all documentation ever written for a system. So you should describe somehow the documentation. We use a special description called DITA. This is the official XML-based schema to describe technical content. And there are authoring tools. So basically imagine all content is not injected from PDFs or Office files. We try to go to the roots. So from content repositories, we are injecting XML-based content, and we need a description. Okay, what is the technical documentation for a network? Not just the content, but the meaning and the structure of the content. So those are the three key elements, and you can imagine that either it is built into an agent or it is loaded when the agent runs from external content sources. Okay. So the next one, I mentioned that this is a semantic execution logic. It means that when an agent is running, when it is triggered, you need to provide some kind of inputs. In a simplest way, an input is just a user message, for sure. But when it is an autonomous agent, it's a system event. It has a structure, and you can define the agent that, okay, what is the structured input? Sometimes it's a let's say it's a data class if you implement it in Python. But sometimes an input can be an agent. Can you imagine when agents are evaluating and checking agents, the input is an agent. And the same way, to make it mirrored, the structure can be just a response, but it can be a structured output or an agent. So you should somehow be generic for the input and the output. And there is another reason where you need to use structured inputs and outputs. When you chain agent, then one agent should be compatible with another agent. So the way you do the compatibility is to define the output structure for an agent, the same, let's say, Pydantic data class, or and the same input for another agent, and then you can easily chain them together. And the problem is that LLMs are really bad at structured outputs. I believe you experienced. So when you just try to drive an LLM to generate some things, you cannot predict, okay, what happens. So you need to somehow structure the outputs. We use the instructor library in Python. I encourage you to explore structured output libraries, because they can force the LLM to follow the structure that we expect. Not just text, but maybe data classes, maybe structured and schematized JSON outputs. So you need to focus on structured I/O as well. Then comes the agent memory problem. So imagine when the agent is running, it should remember. So each agent should get some kind of short-term memory, because it must remember the previous runs, the previous sessions, or if it is a human in the loop agent, that it should remember the conversation. The problem is that if you run different conversations, easily you can go beyond the context window of the LLMs. So you need to come up with some kind of strategy. The simplest way is just to implement the queue. So when the agent is doing his job, you save each entry and you keep it. But if you use it as a context, and for the upcoming conversations you just inject the full queue, you will run out of context easily. So you need some kind of smart approach how to build more sophisticated agent memories. The next option that we experiment with is this LLM-based summary generation. Imagine when the agent is doing something and there is another round, you make a summary. So you ask an LLM to please analyze, okay, what we added, and just keep it as a summarized memory. It's just a short content. Sometimes it's good, sometimes it's bad, but it's add a little bit more complexity for the implementation. More sophisticated way is to implement a vectorizer for the agent memory. What does it mean? You just vectorize all conversations and save it into either a vector DB or an in-memory vector DB engine. And then when you would like to reason about the memory, then you make a vector search. So that's a good one, but it's based on semantic similarity. Sometimes the search can provide relevant memory entries from the vector DB, sometimes not. And probably the most sophisticated is a graph. So imagine that for each run inside the agent implementation, a graph is built, and you are continuously updating a graph, and you connect all the conversations, all the topics, and then you will provide a smart memory for the agent. That's the highest complexity, but the most sophisticated agent memory implementation. Okay, let me go to the next topic, and that's the agent memories. I believe that's at least for us, the hottest topic. How to use a graph, a property graph technology behind an agent. Let me just tell you why you should do that. As I mentioned, if you just try to do a semantic search or just a classic search technology, you cannot make sure that you provide the relevant context with the relationships and the deep contextual information that you need for the agent. So you need a kind of graph technology. I can tell you we use two kind of engines. One is for sure Neo4j. I don't know if you heard about Neo4j. They are creating probably the most popular graph engine. But let me just tell you, there are nice in-memory graph engines, like we use the so-called KuzuDB service that can be embedded to any service. So they are really nice, and they are analytical kind of graph engines. And the idea is that we build different kind of injection pipelines. On the top, you will see the 4 important content sources that we are injecting at the moment. One is the customer documentation content source, and it has this so-called data classification schema. but also we are running code that is building an ontology and a graph from a real system. So imagine we have a pipeline that will check a Kubernetes cluster with all the microservices, all the components, all the interfaces, and all the dependencies, and we are building a graph out of a real system. So this is how we try to mirror the real world to the agents. And we need to build architecture-specific ontologies or schemas. Also, we are injecting functional requirements. They are just telling the agents that, okay, how some feature is implemented and how it is really working. And it is really helping the agent to make decisions. Also, we inject all failures, all bug fixes, all support incidents, and we try to somehow correlate all information inside the graph. So when an agent runs and you ask something from the agent, it will first query the graphs, it will find the relevant nodes, and then it will use graph queries to traverse and get the neighborhood of the relevant nodes from the graphs. So this is what we are doing, and this method is called the GraphRug method. And then you can implement a logic for an agent, like you can see in the bottom. Some engineer can ask the architect agent that please create a checklist to enable a feature for a system components in a certain system. And when this intention gets to an agent, then it will first look up the graph and then traverse the graph. And it will get a really sophisticated context for the agent. So let me just show you how it looks like. So I will switch to a notebook, a Jupyter notebook, and we already injected a lot of content to the graph. And I would like to physically visualize the environment for an agent. So this is a property graph. It is using this KuzuDB engine, and here you can see the true relationship of things behind an agent logic. Red ones are documentation sets, the blue ones are documentations, and the yellow ones, let me just show you another view, just to show you that maybe it's a good idea to switch to a tree view and look at the hierarchical structure of the agent environment in this graph format. The yellow ones are topics of something. Let's check some of the notes I can show you. This is a topic which is called upgrading the firmware using HPC something, and you see a float array, which is the vector representation of the node. And when I was talking to the agent, it was searching the nodes, finding the vector similarities, and getting the neighborhoods of the nodes. So for instance, I have this topic that will tell how to prepare for a firmware change inside the network function. And the blue ones are steps. They are operations. And you can imagine that once we have this information inside the graph, then we can build tools that represent each steps. So hopefully now you can understand why graphs are important for agent operations. Let me just switch to another view. Let's say maybe this circular view. It will show the centrality of the environment and how less relevant nodes are branched out from the central. So this is the most important context for the agents at the moment. And you can imagine that when you are searching, you are just switching different perspectives, and you are, for instance, sometimes you just try to find the top 9 or 5 interesting nodes, and then sometimes you would like to get the neighborhood. Sometimes you would like to traverse the longest path to understand how far you can go inside the graph. And sometimes it's a good context, sometimes it's not. But it's up to the agent and the internal logic of the agent how it is trying to get information from this graph. Oh, by the way, we truly believe that that this is the best, probably the best representation, information representation for intelligence systems. It's a learning curve, I can tell you. But if you have any experience with SQL, then you can just learn a language like here, the so-called Cypher language. That's the international graph query language. So if you start to master the graph query languages, how to define graphs, and you understand how to connect to a graph either in memory or to an external host, I think you are good to go. But it's really an important skill, I can tell you. Okay, so that's the fun with the graph, and let me just go to the next topic, which is the agent toolbox. Inside the agent architecture, we are defining a so-called toolbox, which is a component that can be used to register either built-in tools or external tools. Here you can see the kinds of tools that we need typically in a telco system. So we need tools for the core network functionality. We need API tools. Oh, by the way, I discourage to just take a REST API and just mimic the API as a tool for an agent, because you need to precisely describe what the tool can do, what are the inputs and output parameters, so that the agent can reason, can easily find and understand, okay, how to use the tool. Typically, just to transform an API into a tool, it's not a good approach. And you should think about a little bit that, okay, I have APIs, how they should be represented to certain agents. So they are not just a direct wrappers for API tools. For platform tools, if you use the GitHub copilots, or the agents in GitHub or Windsurf or Cursor or any agentic tool, you saw that how agents are doing their jobs. Inside each agent, they are using a platform and environment tools. They can edit files, they can run commands, they can write bash scripts, they can even dynamically write Python code and execute Python code and get the results and take the responses to the execution. And also there are productivity tools. For instance, we would like to build tools that can easily do explorative data analysis for any tabular data sets. It's a very typical scenario. You get a log file, you need to read it to memory, and you need to explore what's inside, maybe do some machine learning logic over the data. But they are really key, and we use a command architecture patterns inside the agent architecture, meaning that it's easy to, by configuration, change agent and add or remove agents. And also we try to build not all the agent, but as much agent into MCP clients. So we believe that we won't be responsible, or we cannot build all the tools that we need. Maybe someone else will build the tools, and we try to make the architecture flexible to connect to external tools. And I believe that the model context protocols will be the standard for the future. Okay, and really the last topic, the worker logic, and that's a key learning as well. As I mentioned, you need to build a special logic that is combining LLM calls with classic native code. It's unavoidable. So if you really want to build an agent that is smart enough, like a human, to analyze, plan, and execute something, then you need to combine, and for each agent, yes, you need to implement a worker logic, so that when you analyze, then you understand the intent. And also, you check a lot of things. So sometimes an agent cannot perform an operation because there are no information available to complete a goal, for instance. And also, you need different strategies, not just how to analyze, but to plan an execution. Maybe the agent is not provided with enough tools, and maybe an agent can need to make the decision to work with another agent. So that's a totally different strategy, and each agent should be flexible to use different worker logic. Okay. And also, you need to be prepared that sometimes you are calling LLMs, but many times it is just simple native logic. It's unavoidable. All right, so that's my content for you today. I hope you enjoyed this introduction and the complexities of agent architectures. If you are interested in discussing, then you can reach out to me via LinkedIn. And I'm curious what you guys are building. So thanks for coming, and I'm open to discussions.
All right, thank you very much. For the last time today on this stage, here's the QR code for the questions. We have time for 1 or 2 questions. So if you have any that you'd like to get answered now, okay, we already have one, very quick. So the first question, how do you evaluate agents?
Yeah, it's a good one. We will evaluate with humans, domain experts, but also we try to build evaluator agents. So if we can, we will build custom quality assurance agents that will check other agents. That's the plan. But you should be prepared that you will need to talk to domain experts, because you would like to provide the same intelligence for agents, and you do need experts to come up with the real meaningful questions, the real meaningful intentions and goals for agents, and they need to provide the real responses. By the way, you can automate this, so it can be just an Excel file and an evaluator agent that is asking the questions and getting the responses and comparing the agent responses to the human responses, and provides a quality score for the evaluation.
All right, thank you very much. Let's see if any other questions come in. 3, 2, 1, go. It seems no. All right, a big round of applause for our presenter. Thank you very much.